So for today, I do have a tutorial, right? So we will go to it in a moment. But I think today we are going to talk a bit about matrices, right? So I think I'm going to go through most of the class on the board today, okay? So now there's a tutorial, we will go through it in a bit, okay? But not right away, okay? Okay. Before that, do you have any questions, comments from previous classes, or no issue so far? Okay, so let's do this. Yeah, there's a computers. Got stuck. I don't know. Well, doesn't matter. Okay. So what are we going to talk about today is we're going to talk about matrix models. Okay, matrix models. So these are. I think it's better to start with this one. Yeah. Okay. So we're going to start with talking about matrix models. Okay. And the idea of this is when you have a population that you want to take into account age structure, okay? So what is age structure, right? So you have a population, but you subdivide the population according to age, okay? So you have juveniles, you have newborns, you have, for instance, if you have insects, you have eggs, nymphae, larvae, adults, and so on, okay? If you have plants, annual plants, then you have new individuals and older individuals and so on, or if you have, or even with mammals, right, that usually we think in terms of, you can also have divide them by age, okay, 1 year, 2 years, 3 years, and so on, right, and you see from my thought here that I'm already simplifying quite a bit the problem, because I'm not trying to keep track of the exact age of each individual, right? I'm going to, so here, our first treatment will be in discrete time, okay, using discrete time steps, okay? So I'm going to say that there are first year individuals, second year individuals, third year individuals, okay? So I will classify, I will classify each individual by age, and I will track the population, not just the whole population, but also the population of each age, okay? Yeah, does that make sense? Yeah? Okay? And I will start this with a discrete model as well, right? So that when I advance 1 year, the individuals that were from the first year will move to the second year. Yeah, does that make sense? So we have for discrete models. So discrete models, let's just or mappings or recurrence equations, right? We had something like this before, right? So we had something like, we had expressions like this, okay? Yeah? Like the discrete logistic equation and so on, the geometric growth rate, okay? Geometric growth equation, you remember this more or less, yeah? Okay, so now I want to do a model that is a generalization of this in the sense that I'm going to write something like, for instance, let's use 3 classes, okay? 3 classes. So I will put newborns, juveniles, and adults, okay? Adults, okay, here. Okay, and I want to write equations for these guys over here, okay? How do I do that? So I will say that at the next time step, the next year, how many newborns do I have? How many newborns? Okay, in the next year, okay, so I have the number of newborns, juveniles, and adults at time t, okay, at this year. And I want to know how many newborns I have in the next year, okay? Okay, the newborns from this year, next year will already be juveniles, okay? Yeah? And I'm going to assume that also juveniles only take 1 year to mature into adults, okay? So all newborns will become juveniles, all juveniles will become adults, okay? And then the only newborns around will be the new newborns, okay? The new individuals that depends on reproduction, okay? Reproduction, right? So I'm assuming also that only those are only ones that reproduce, okay? Only adults reproduce. Okay, so this is an assumption here. Okay. Okay, so my model will be something like this. So I'll have that n at time t plus 1 will be proportional to the number of adults. Suppose that each adult has some fecundity per year. This will be, so the total number of newborns are going to be proportional to the number of adults at the previous year. Does that make sense? Yeah? Okay, so this is going to be B times A at the time T, okay, at the previous generation, okay? How many juveniles am I going to have? Can anyone make a guess here? Yeah? It's just the number of newborns, right? Before. But some of them may not survive, yeah? Some of them may not survive. So I include something here that is the survivorship of newborns, okay? Times the number of newborns. Yeah, of course, this number has to be between 0 and 1, right? Because this is a survival, okay? So if half of them die during this year, I have half here. If 10% die, I have 0.9 here. Yes? Question? Mike. Where are the mics? Oh, there's one over there already. Yeah. Ah.
It wasn't, it was just for you to repeat what was the A and the B in the newborn.
Sorry?
What is the A and the B in the newborn equation?
Okay, the newborn is, okay, so I'm here today, I have a number of newborns, juveniles, and adults. I want to know the number of newborns of the next year, okay? So the newborns today will not be newborns next year, right? So the newborns of the next year will be the ones that are generated by the current adult. So B is the fecundity, okay? So this is, yeah, this is the fecundity, okay? Or the reproduction rate, something like that, okay? This is the fecundity, okay? And the newborns that were already here today, right? Next year they will already be juveniles, okay? Question?
So for the juveniles, we are considering that all newborns from the past generation are now juveniles. So after one generation...
Exactly. So I'm saying that these are first-year individuals, first-year individuals. These are second-year individuals, and adults are more than 2 years, okay? More than 2 years old.
Yeah, sure.
Yeah?
I get that this is like a generalized model, but how do we account for species that in less than one generation, the newborns are already juveniles?
Sorry, can you repeat?
I mean, the newborns can be juveniles in less than one generation, I guess, in different species.
Oh, yeah, you're
so
saying,
how do we account for that?
Yeah, so we would of course, because here I'm taking time steps of 1 year, okay? You see that a generation here, this model, let me just finish the model and then I'll go back to this, okay? Because this looks like it's going to be a discrete generation kind of thing, but that's not exactly true in the end, okay? So let's now go for the, but for this is okay, so far these equations, with the assumptions I have told you so far. Yeah, I know you have some questions for something a little bit different, okay? But for this, okay, so far? Okay, so let's now write the equation for adults, okay? Adults. So the adults of the next year will be the juveniles that survive it, okay? Just as before. So I have here juveniles that survive it, But I didn't tell you that adults live only for a single year. Maybe they live longer, okay? And if they live longer, there are also a few adults from the previous year in the following year, okay? So I have here also the surviving adults from previous year, okay? Good. Okay, so these are my three equations, okay? Yeah? Are you okay with this? Okay. Now so you see here, so for your question now, right? So here I took time steps of 1 year, okay? I could have taken smaller time steps, okay? So it would instead of putting 1 year, would take it time steps of, I don't know, 1 month, or usually you take a time step that is as small as the smallest transition, right? So if juveniles, if newborns become juveniles in 3 months, I don't want my model to take a time step of 1 year. You see, I want it to take a time step of 3 months only. Yeah. So I always adapt my time step to be appropriate to the scale of the problem I want, right? But then, what if maybe your question was not exactly that? I'm not so sure, but then what if I want for instance, suppose my juveniles, I don't know, this takes like 1 year, but then from juveniles to adults it takes, I don't know, 5 years, right? So you have to spend a long time here. Do I need to write down juveniles of the first year, second, third, and fourth, and fifth, and so on? No, right? So what I do is that I write something similar to this here, okay? I say that juveniles stay here for some time, okay? And they have a chance of changing classes for adults with it's an end of survival, but here when you don't survive, there's a probability of staying as a juvenile or maturing into adults, okay? And this probability, if I don't know if this is like 5 years, it should be 20%, okay? At each year, 1/5 of the population is going to move to the next class. Does that make sense? Yeah? Yeah? Okay, good. Okay, but, and this is kind of discrete time, discrete age structure, right? So we have time is moving year by year, and you have the only 3 classes over here. But you see that different generations are not so well defined, because you see that adults, they mix, right? So a population, so for instance, I start at time 0, okay? And then I'll have some just newborns at time 0, and then juveniles, and then adults, and these adults will produce newborns and so on. But some adults from the first generation will stay for a long time, okay? They will survive for several years. So, and then they will reproduce together with some adults from the following years. So the generations in this model, they do mix, okay? They do mix, yeah? Yeah, clear? Okay, so this is not exactly as this equation tells, that really discrete generations, because here I do allow generations to mix, okay? Because adults from different generations are reproducing together, yeah? Okay, good. Now let's make an example here. So I copy the values of parameters that I had here. Over here, yeah. Just so the calculations are easy, right? So how do I solve this? Okay, this is very simple, right? So let's take an example. I put here b equals to 4. So let's take an example here. Okay, so b equals to 4. I put the survivals of juveniles and newborns at 3/4, okay? And the survival of adults at half, okay? A half, and then I put an initial condition. So to start this, to run this, I also need an initial condition, right? And I put only adults at the beginning, right? So I put a equals to 8, a at time 0, 8, and n and j at time 0 at 0, okay? So these are initial conditions. Initial conditions. And these are the parameters, okay? Over here. Okay, so this is just for an example, okay? So what is going to happen with this situation here? So I start at the first generation, there's only 8 adults, okay? What happens in the second generation? This is simple to do, right? Yeah, yes or no? Yeah, so what is going to be N1, J1, and A1? Yeah, N1 is how much? How many newborns I have in the next year? No clue? What? 32, right? Yeah, so I have 8 adults. They will have, each of them, they will have 4 newborns, okay? So I have 42 here, okay? And how many juveniles? 0, right? I don't have any newborns here, so I have no juveniles. How many adults? 4. Why 4? I don't have any juveniles at the beginning, so none of them are going to mature into adults. But I have 8 adults, and half of them survive. Okay, half of them survive. So I have 4. Okay. Okay. So I did one step here. Now let's do another step. So N2, J2, A2. Okay. What is this like? Okay. So N2, right? What is this? I have each adult giving 4 newborns. I have 16 over here, yeah? 16. J2, what is J2 here? Is the number of juveniles at the second generation is the number of newborns at the first generation, right? But only the ones that survive, yeah? So I have 42, 1/4 of them die. Then I have only 24 left, yeah? 34 over here. And what is A2 now, right? So I didn't have any juveniles, so I still don't have any juveniles maturing into adults yet, right? So I only have the adults that survived from before, right? So I have 2 here, okay? Yeah, okay, people. So is this easy, clear, no questions at all? This should be easy, right? Yeah? Yes or no? Comments, questions? Yeah, yeah? Okay, okay, good. So I want to do this now in a slightly different way, okay? I want to do this in a slightly different way. Of course, we can do it like this. We can just using this as if they were 3 equations, okay? But I want to notice that you see that all terms here, they're just proportional to A and J, okay? They are all linear terms, okay? So there's a smarter way to write this out. That is in terms of a matrix, okay? So I'll write this in the following way. I will write a vector, okay, xt, that is going to be nt, jt, at, okay? So this is a vector, okay? And then my equation over here, okay? Instead of writing it in this form, I want to write it as a product of 2 matrices, okay, or a matrix with a vector, okay? So I'm going to write it. I will write it for you, and then we can open it to check that this is true, okay? So this is 0, 0, b. This is going to be Sn 0, 0. This is going to be, now for A, this is going to be 0, Sj, Sa. Okay? So I'll tell this matrix here, I'll tell it M, okay? Times my Nt, Jt, At over here, okay? That is, this is M multiplied by X at time t, okay? So, okay, so now I wrote this as a product of this matrix times this vector. So to really make sense of this, we have to remember how to make products of 2 matrices, okay? Yeah, everyone remembers that. I think people from biology, it takes a long time It was a long time ago, right? Yeah, so let's calculate this product over here, okay? So do you remember how to do a product of two matrices? Yes? No? Don't remember. Okay, so, okay, no, it's no problem. I took time for this, okay? No, I'm not, oh, I wasn't too smart because now when I move, yeah, I should have started with the board over there. Yeah, okay, sorry. But maybe if I just do this, is okay? Not so much, sorry. Yeah, so maybe I just copy this matrix over here. So we want to multiply this matrix over here. So this is 0, 0, B. This is Sn 0, 0. And this is 0, Sj, Sj, Sa, okay? Times Nja, okay? Nja. So what was the usual way to do this, right? You put the first one over here and the other one down here, okay? Yeah? Yeah, I don't need this indexes right now, okay? Yeah? And then what do? Okay, the first element here, okay? So this is 3 by 3, this is 3 by 1, right? 3 lines, 1 column. So the result will be 3 by 1, right? Just writing it like this, you already know the shape of the result, okay? So this is 3 by 3, this is 3 by 1, so the result will also be 3 lines, 1 column, okay? And then the first element, what is in the first element over here, right? So, so we have to go over the lines here and the columns here, okay? So I take this here, I go m times 0 plus j times 0 plus b times a, okay? This is the first element. Now the second element here is second line, first column. So I take the second line of this matrix with the first column of this, and I go Sn times n. Oh, oops. Times n, okay? Plus 0 times j plus 0 times a. Okay? Yeah, and then the third one, I go 0 times n, Sj times j, plus Sa times a. Okay, and this is the result. Okay, I can simplify this, okay, because there are a lot of zeros here. So I'll have Ba, Snn, and Sjj plus Sa, Sa times A, okay? And this is exactly my model equations, right? So this is, yeah, let me put the t back here, okay? So, and this is my new vector, okay? You see here, B times A, Sn times n, Sj times j plus Sa times A, you see? And these are the 3 elements of the new vector, the vector for the populations at the time t plus 1, yeah? Easy, not so easy? Questions? Yeah? Okay, so, good. Before moving on, right, so I think we're going to use a lot of matrix products in the next classes, okay? So instead of moving on right now, right, so I want to maybe go into a bit more detail on product matrices, okay? Product between 2 matrices, okay? So I want you to think of this in a more general term, okay? So, instead of just, so let's do this in a more general way. What is a more general way? Instead of using these particular values here, okay, let's write a general matrix, okay? So let's write a general matrix. So I have, what if I had, instead of this, I had a full matrix here. So I have A11, A12, A13, okay? And just see here that the two indexes here, the first one is for the line, and the second one is for the column, okay? Okay, looks like this, yeah? Multiplied by a vector, okay? I tell this x1, x2, x3, okay? Over here, yeah? So this is just because here I have a lot of zeros, a lot of cancellations and so on, right? But I want you to look at the expression of the result and be more familiar with that, okay? Be familiar with that. So what is this, right? So it's the same thing as we did here, okay? So I will take for each element here, right? So what is going on here? So I have, I'll tell this matrix here A, okay, large A. And this is vector x, okay? This is vector, I'll tell x, okay? So this is the x vector, okay? And I'll tell this result, I don't know, I'll tell this result y, okay? Y. And let's write down what happens here, okay? So I do the same calculation. I think this is simple now, yes or no? Yeah? So A11, x1, A12, x2, A13, x3, right? So let me write this a little bit faster, okay? And now the second line here, A21, x1, A22, x2, A23, x3, okay? And that last line is pretty much the same, okay? So I have A31, x1, plus A32, x2, plus A33, x3, okay? Okay. So what is going on here? So this here, I call this y, okay? So this will be my vector defined by y1, y2, y3, okay? Okay. Right, so what I did here is that I calculated, let me divide the board here. So the calculation that I did here was calculating A times the vector x equal to the vector y, okay? The result of this is y, okay? Okay. What happens here is that when I want to think of this in terms of the indexes, okay? What is the element let me call this ye over here, yi, okay? Or maybe let's take the y1, okay? Y1 is A11 x1, A12 x2, A13 x3, right? And y2 is h1 x1, h2 x2, h3 x3. What is the difference between y1 and y2? In terms of the indexes, okay? The line that I took from the matrix A, okay? So everything's the same from the first to the second to the third line, except for which line I took from the matrix A, okay? So here I took the first line. So the indexes of A here, the first index is 1. Here the first index is 2. And here the first index is 3, okay? And all the rest, what is it? It's just a sum of varying the columns here together with the lines of x, okay? So what is y1, right? So it's the sum of A1j times xj, with j going from 1 to 3. Yeah? So this is a summation here where j takes the values 1 to 3. So I have A11 x1 plus A12 x2, A13 x3, right? So I just put a comma here to make it clearer, right? That is two different indexes, okay? Not always necessary, but sometimes it makes it clearer, yeah? Easy or not? So then now we can, instead of looking for y1, this expression will be the same for the second line and the third line, right? So y2 is a2j xj, okay? And y3 is a3j xj, right? So if I take some general yi, it's going to be aij xj, okay? And this is the expression that I wanted, right? So this is the general expression for matrix product in terms of indices, yeah? Okay, so sometimes it's easier to think in terms of this, right? In terms of this multiplication, but sometimes you see stuff in terms of indices and recognize that this is exactly the same thing as this, okay? So these are synonymous, yeah? Of course, this has to be true for every I, right? So for I equals to 1, 2, 3, right? So for I equal to 1, 2, and 3, yeah? Okay? Yeah, so this is a refresher on matrices, right? So for products among matrices, okay? Good, yeah? Questions, comments? Okay, good. So, so what are we going to do now, right? So we were just representing our matrix model in this form here, right? So, yeah, I have to now. Oh no, it's time to erase this part of the board. Yeah, good. So I want to write this model here in that way. Okay. So let me erase this part here. And then, what do we have now, right? So I did this stuff here in order to write my model in this way, right? So now I have xc plus 1 is just m times xc, okay? So let me rewrite this, right? So xc plus 1 equals m. Maybe I show back here since you're still maybe looking at it, yeah? Yeah, m times xc, okay? What is so nice about this? The thing that is really nice about this is that now it's easy to understand what is the answer, right? What is the full solution, okay? Because what goes on here? So the initial condition is some given value of x0, okay? That I put it equal to 0, 0, 8, right, in our example, yeah? Okay, I started with 8 adults. This means 0 was 0, 0, 8, okay? And then to calculate x1, I have to take m times x0. And then to calculate x2, I have m times x1. But x1, what was x1? It's m times x0, right? So this is m times x0, right? But I have a multiplication of matrices. I don't have to multiply this first and then this. I can just put these two together, right? So this is just m squared x0, right? So instead of making this product and then this, I can take the product of these two matrices, m squared, and then multiply by x0, okay? And then for x3, it's pretty much the same, right? So x3 is m times x2, okay? But then x2 is m squared times x0, so multiplied by this m here, x3 will be m cubed times x0, okay? So you see that, don't you remember this? It's pretty similar to what we did also with geometric growth, yeah? If I have, you remembered with this equation like this, and we have this equation here with a single population, right? Yeah? What was the general solution for this? It was something like xt is equal to r to the power t times 0, right? So this is exactly the same, right? So at the time t over here, at some general time t, at the time t will be the power t, m to the power t times 0. Right? What is the difference between that thing here? Okay, this is geometric growth, right? So this is a geometric progression, right? So if I have r equals to 2, I have 2, 4, 8, 16, 32, and so on. This is a geometric progression. Now this is not so simple, right? This is not so simple because this is m now is a matrix, okay? And what happens when I keep multiplying by the same matrix over and over and over, okay? So this is what we want to explore a bit today, okay? Yeah? Questions? Okay, so with that said, now I want to go to the tutorial, okay? To the tutorial. So let's okay. So let's change over here. So I have more or less repeated a bit the parts that I talked about in the board, right? But I think it's better to write in the board rather than just reading what I wrote, right? Yeah? Okay, so I think it's clearer. Yeah? So this is pretty much what we have discussed. And here, now we are going to implement those equations, right? So what do we do, right? So we write the initial condition, we write the parameters here, and now we shape our matrix here using a 2D array, okay? And here you see 0, 0b, Sn 0, 0, 0, Sj, Sa, okay? And now how do I do a matrix product using NumPy, right? So we have discussed this before, right? Instead of, if you do just asterisk, it doesn't do the matrix product. It does an element by element product, okay? So what we want instead is to use this method called dot, okay? So m dot 0 does the matrix product, all right? So let me go step by step here. How do I run just this code again? So run selection, Ctrl Shift Enter. Okay, so I don't go up until the end, right? So let's do this. Yeah. So I'm just running this part of the code over here, right? So it takes some time to import everything and so on. So is it clear what I did here in the code or not? Yeah? Okay, so just define an m, define the parameters, define the initial condition. These are the same values that I used on the board, okay? And now I do one iteration, okay? I just calculate this, if this is at 0, this will be at 1, okay? So I have now only 4 adults and 42 newborns, okay? Now if I do this again, right? So I take the previous x and then I calculate m times this previous x. I have now 16, 24, and 2, right? And if I do it once again, what do I do? What happens, right? So this is now 8, 12, and 18. Okay, I think we didn't go up to this step on the board, yeah? And of course, I can keep going, right? So how do I keep going for some number of steps? I just do a for loop that keeps repeating this calculation of multiplying x by m, right? M dot x here. I assign to x the new value and I keep printing it, okay? If I do this, now let me run everything, right? So this is the initial condition that I didn't print, then the first one, the second, the third, now the fourth, fifth, sixth, and so on, right? So I can do this any number of times, yeah? Easy, right? Easy. Yeah? So I think by now we have done a lot of more complicated things, yeah? Okay, so of course I want the full solution, right? So let's do this in a more, in a smarter way, right? So how did we solve recurrence equations? We had a list, right? In the list we had the initial condition. I define a range of times, okay? And now I already have the first, so for t equals to 0, right? For t equals to 0, I already have the initial condition, so I don't have to step over all t's, only the number of t's minus 1, right? Yeah? And then for each time step, I append to this list m times the last value of the array X, okay? Yeah? Okay, so I start with X 0. Okay, so now X minus 1, the last element is at 0 in the first step. I append a new one to this list. And then in the next time step, I append the next one taking the last element, m times the last element, and so on, okay? Yeah, so this is pretty similar to that when we solved the reverse equation, yeah? Good, so then in the end, I have a list, and each element of the list is an array with 3 elements, okay? So with the 3 values of the population, yeah? Population for newborns, juveniles, and adults. And then I convert it to an array, right? So that I can manipulate that easily, and let's run this and try to print it, right? So I had 10 time steps here. So I have a matrix that is 10 by 3, right? So 10 lines, 1 for each time, and 3 columns. So for newborns, juveniles, and adults. And now I see exactly the same numbers that I printed before, right? So I have 0, 0, 8, 42, 0, 4, 16, 24, 2, and so on, right? So, yeah? Good, yeah? And then we can plot this, okay? We can plot this as we have been doing, right? So the plot of this looks like this. Now this is a bit funny, right? Yeah, why is that funny? The population doesn't simply grow, right? Because, you know, you start here, you have only a single adult, not a single, 8 adults here, and N and J are 0, okay? But then the adults decrease, and then they increase again, and then they decrease, and then they increase, and then they decrease a bit, and so on, right? And then the same for newborns and juveniles. You see that the general direction is that they are increasing, they are growing, but they're not like growing just growing, right? So they're oscillating a bit, right? Yeah, this is funny. Yeah, this is kind of funny, right? So you see that products by matrices are not so straightforward as in the single equation with just a number, where you either just grow or you just decrease always. Okay? Yeah. Here we have that the general trend is increasing, but there are some oscillations there. Okay. So I want now for you to try to work on this a little bit, right? So I want you to look at the total population. So how do you do total population with this thing here? I have to sum the 3 columns. Okay, if I sum the 3 columns, I have the total population, right? Yeah. So if I sum it, so I want you to see what happens for a large time. For a large time, what happens with the total population? Instead of looking for each population, I want you to look at the total population. Okay, and especially, of course, we more or less know the answer already, right? So this is just growing and growing without limits. Okay, the population is going to explode. Okay, yeah. So don't take a too large A times A, otherwise, yeah, don't take T or going up to, I don't know, 1,000, because it will be a bad idea. Okay, but I want you to explore this and maybe try to see what is happening, plotting a large scale. Maybe you can calculate not only saying that it's growing, but maybe also calculate the rate at which it is growing. Okay, looking at the total population. Okay, so this is the first question, and then I want you to check. Well, what if I change the parameters? Okay, what if I does the population always grow like that, or depends on the parameters? Are there parameters for which the population doesn't grow? Maybe the population goes extinct. Okay, I think this is kind of obvious, right? If I don't have any newborns, okay, if I put the fecundity to 0 or some very small value, of course the population is not going to survive, right? Yeah. Okay, so this is kind of obvious, but is it possible to have something else? Is it possible for an equilibrium population? Huh? Yeah, what do you think? It's kind of weird, right? Yeah, I don't know. Do you have any clue? So maybe let's try try varying the parameters. Okay, you can vary all of them. Okay, but I think it's easier to just vary the fecundity. I think it's the easier one to manipulate. Okay, don't try to vary all of them, because it's just yeah, kind of Yeah, you can try, of course, yeah, so is your question, right? And then a final question here is what happens to the relative proportions, okay? So we see in this plot here that at the beginning you have many adults to know, or adults should know juveniles and adults, but as time goes on, sometimes you have a lot of adults and very little juveniles and newborns. And at other times I have few adults, too many juveniles and newborns, okay? And this keeps changing here in the beginning, okay? So I want you to check, or maybe try to plot this. How do you plot the proportion, right? So you take the total population, and you take each class, right? Each N, J, and A, and you divide it by the total population, right? So that you can see the fraction, or the proportion of the total population of each class, okay? Of each stage. Does that make sense? Yeah? So try plotting this over time and see what happens to the proportions of each stage, okay? Okay, so this is time for exercise now, okay? So I'll give you some time to do it. Yeah. Okay, so let's try to do this over here. Okay, so okay. So total population, right? So I'll just copy the codes that I had before, right? So let's copy this part here, okay? And then I will put it a larger time here, I don't know, 50 times, okay? And then what I want at the end, okay, I won't print it. What I want at the end is, well, X has 3 columns. I want the sum of the 3 columns, okay? So I will say that the total population here is going to be the sum of the first column plus the second column plus the third column. Okay, so this is a simple way to do this. We can also, instead of doing that, there's a sum method that you also have used. So you could also write this as sum of x over the axis of the columns. Okay, so this is the same as over here. Okay, so you remember when we took the minimum and the maximum, right? So we wanted the minimum and the maximum over each column. So we took with x is equal 1. Now I don't want to sum over each column. I want to sum over each line, and then I use x is equal to 1 over here. So this two here, they are the same, right? So let me just check this. So let me comment this one. So you see 0, no 8, 36, and so on and so on. If I comment this one and have this one, you see 7.28, 10 to the 9, and so on. You see that it's the same result. Yeah, so doesn't matter. Okay, so you do the way that you like best. Okay, so this is the total population, and now I want to plot this over time, right? So I want to plot this over time. So I just let me do this in a new cell over here, so I don't need this legend anymore. All right, so this is the total population, and just see that. Oops, sorry. I plotted x, not the total population over here. Okay, so this is just increasing. You see that this is going to 10 to 9. Okay, so this is 7 million. Okay, 6 million, and so on. Right. So this is increasing. Looks exponential, right? So how do we check that it's actually exponential? We put the y scale, the y-axis scale, in a log scale. Okay, and then we see that it fluctuates a bit in the beginning for the first few iterations, but then it goes through a straight line. Okay, so if this is a straight line in a plot with the y scale is log, then this is exponential growth. Yeah, exponential growth. So we see that we have exponential growth, but then can we do something better here, even better? We could also try to, you see here the total populations, right? We could also ask, what is the growth rate? Yeah? What is the growth rate? How do I measure the growth rate? You can divide the population at one time step by the population at the previous time step. Yeah? Okay? So I'll take pop total here, and I want for each pop total, so I'm going to do a bit of a trick here. So I want for each pop total to divide it by the pop total in the previous time step, yeah? So what do? Of course, the first one, I cannot divide it by the previous one, so I have to skip the first one, right? So this is the vector, this is this vector starting at the second element, and I want to divide this by the same vector starting with the first element and without the last one, right? So I just divide pop total like this by pop total without the last one. Yeah? And this is the growth at each generation. Does that make sense, people? Does that, yeah? Yes or no? Okay, so I divide this by this, and you see that it starts at a high growth rate, and then it keeps changing. It's changing, okay? So maybe let's maybe write in this way, right? So growth, and then I will just plot, okay? So let me plot this over time, okay? And you see, it oscillates a bit, but after some generations here, about 20, it stabilizes, okay? It stabilizes. So the growth per generation of the total population goes to a certain value here. Let me print growth again to see what this value is, right? So yeah, so it is approaching 1.5, right? Yeah, you see here in the end, 1.5, 1.5, 1.499, 1.499, 1.5, 1. Yeah, so it's getting close to 1.5. Yeah, yes. Sorry, I don't hear. I think I hear. Sorry, I'm very, very, very deaf. Can you repeat with the mic? Yeah.
Okay, in the third one, we have to do the same growth equation, but for the three of them. Yeah.
Yeah. I'll get there in a bit. Yeah. Yeah. But then I want to look at the relative proportions instead of the total population. Yeah. So. Oh, okay. Sorry. Okay. I thought you were asking about this. Okay. So. Questions about this? Is this clear? Yeah. So here dividing the total population by the previous total population, the previous generation, we see that after some time we stabilize at a growth rate per generation of 1.5. Okay. You see that even for the fecundity here was 4. Okay. I have losses, right? I have losses due to survival not being 100%, right? So I only one fourth of the newborns die, and then 1/4 of the juveniles die before getting to adulthood, and then the stable growth rate for a long time is just 1.5, it's not 4, okay? It makes sense, right? Yeah? Yeah, not all juveniles, not all newborns will grow up to be adults, okay? Good, so okay, what we do now, right? So now I want you to check if all of this is still true, if I have different parameters, right? So what I'm going to do here is just to put all of this again over here. Let me plot this together. Over here, without printing the total population. I have the plot already, but then I want to change the parameters, okay? So before doing this, I want to redefine the parameters over here, right? So oops, I want to copy this over there. Right? Yeah, over here. So before all of this, I redefine the matrix. Okay, so what happens if I increase the growth rate? Okay, then it's just going to grow even faster. Okay, so we can check this by running this calculation over here. Yeah. So so down here, I run again this growth calculation, and you see that now I'm growing at 1.68 after a long time, yeah? So it's growing faster. So if I keep reducing now, if I reduce the fecundity by a little bit, right? For 3, I still have some growth. Now, yeah, let me print just the last one, right? I think the last one is enough, right? So, yeah. So now 1.48 here in the end, yeah? So it's growing a bit less, okay? And now if I reduce B to 2, what happens? I'm still growing, but now with I don't know where exactly it changes, but now it's only 1.2, right? So maybe let's go to 1 already, B goes to 1, right? So each adult leaves only a single newborn, okay? Now it is still growing, but now with a growth rate of 1.03, right? So this is very close to extinction, right? Yeah. You see, each adult lives 1 newborn per year, right? But adults live for several years, so they can live more than. Of course, if there was only 1 for the whole lifetime of the adult, this would already be extinction. But since adults can live for more than 1 year, this doesn't happen, right? So now with B goes to 0.6, we now have extinction, right? So the population is decreasing, okay? It's decreasing, yeah? But even when it is decreasing, we still see that the growth rate is now below 1, right? So this means that the population decreases by 10% each year, okay? And it's decreasing at a stable rate as well, yeah? Okay, so this is always works like this, even for population decreasing, okay? And of course, it's very hard to find equilibrium, okay? Equilibrium. You usually always have either exponential growth or exponential decay, right? There's exactly a single value where there's equilibrium that corresponds in this model here for geometric growth, corresponds to when R is exactly equal to 1, okay? But this, of course, in nature doesn't really happen, okay? Because you have to have the exact value, okay? Of course, exponential growth doesn't happen in nature forever either, right? So it may happen only for short times. Okay? Questions? Yes? Is that clear, or is it you got to this part already, or more or less? Yeah? Yeah? Okay. I think the harder part was to calculate the growth rates. Yeah? That was a bit more tricky. Okay. But now let's look at the relative proportions, right? So let me copy all of this again. But now let me go back to the original parameter with B equals to 4 over here, right? And now what I want is I want the relative proportions, okay? I want the relative proportions. So now, instead of having x, right, I will say that x0, the first column, I don't want it to be the total population, but I want it to be the population relative to the total population. So I'm going to say that x0 will be now x0 divided by the total population. Yeah, and the same thing for x1 and x2. Okay, so I want this to be the proportions. Okay, so I take I want the x0 now to be the newborns divided by the total population. The juveniles will be the juveniles divided by the total population, and the same for the adults, okay? So now x no longer represents the total population, but the proportion of each class inside the population, okay? Yeah, and now what I want to plot here is now x, okay? It's now x, the proportions, okay? I don't need this y scale, but I do want the legends back. Where are the legends? Yeah, over here, okay? And now the legend over here. What is going to happen? You remember that we had a lot of oscillations, right? Yeah, so we see that, okay, the sum of the 3 lines at each point is going to be 1, right? Because if you sum the contribution of each population, it has to give you the total population, that is 1, okay? So these are the fractions that sum to 1, and then they oscillate a lot in the beginning, as we have seen right in the beginning. They do oscillate a lot, right? But after a long time, okay, after some time here, some close to 20 generations, they stop oscillating, and they reach a stable state, you see, where these proportions are constant over time, yeah? you see that this A of time is more or less also this A of time that it takes for the growth rate. This was for B goes to 4, right? B goes to 4 was over here, yeah. Yeah, more or less about the same time that the growth rate also stabilizes, you see? So more or less the same time that it takes for oscillations in between sizes of the different classes to stabilize, it's also the time that it takes for the growth rate to also stabilize, okay? Nice, yeah. So you see, even for at the beginning it looks crazy, it looks like now you have a lot of adults, now you have a lot of juveniles, a lot of newborns, and so on and so on. For a large time, over 20 generations, this goes to a stable age distribution. Yeah, so this is what this is. Oh, this is the stable age distribution. Okay, so this model is not. There's no equilibrium in the sense of a fixed point. It's just exponential growth. But even exponential growth has some structure, right? So the growth rates are constant, and the distribution among the different classes, the different ages, also becomes stable. They are always proportional. Okay, so all of them are increasing at the same growth rate. Right, it was 1.5, so all three classes now are increasing by 1.5 each generation, and their proportions remain the same. Yeah, nice. Did you expect something like that or not? Don't know? Yeah? Questions, comments? No? All clear? Okay, so I have a final comment here, okay, that is how this stuff that we have just seen is related to the famous eigenvalues and eigenvectors, okay? So if you have followed this, now this is what I explained in the boards, right? So when you have a matrix that is iterated, multiplied many times, right? This is pretty much always what happens, right? So applying a matrix many times, right? The structure of this m to power n, right, with n large, is always going to lead to something that it is all this product is always dominated by what we call the main eigenvalue, the principal eigenvalue, the eigenvalue of this matrix that has the largest real part, okay, the largest value, okay. So so just so in this example here, the growth rate per generation is the eigenvalue of this matrix, and this stable age distribution here, right, the proportion of n to j to a is the eigenvector corresponding to this eigenvalue. So it's the proportion of the proportion of population for each age structure that gives you this given growth rate. Yeah, so I don't want to go too much into what are the mathematical definition of eigenvalues and eigenvectors, but you can think about it in this way. If I have a matrix product, something that is repeated over and over and over, eventually the growth rate is the eigenvalue, the principal eigenvalue, and the age distribution, the stable age distribution, is the corresponding eigenvector. Okay, so this is even if you don't know the math, you can have a feeling for what eigenvalues and eigenvectors mean in terms of population growth. Yeah. Okay. Now I have some details here. So you can, of course, you can take this matrix, okay, and you can calculate it directly, right? You don't have to multiply. You don't have to multiply and then take the growth rate and plot this. You can go directly to the matrix. Okay, I take the matrix, and now NumPy already has inside its linear algebra module. It has this ig function that can calculate the eigenvalues of eigenvectors for you. Okay, it does that numerically. So you see there are three eigenvalues. The first two, this part here with this j, is an imaginary part, right? And when you see an imaginary part in an eigenvalue, usually you see oscillations, right? So at the beginning, we saw that there were large oscillations, but the largest eigenvalue has zero imaginary part, right? So what is its value? Exactly 1.5, right? So looking at this, I see that the eigenvalue with largest value is this one. So for a large time, the growth rate will be 1.5. Yeah, nice, right? So I didn't have to do all the calculation. Just look at the eigenvalues and say, wow, 1.5, it means the population after a long time will grow with a rate of 1.5 per generation. Yeah, nice. And now the other thing that this id here returns, the second part of this id here, the second element, is a matrix where each column is the eigenvector, okay, the eigenvector. So the eigenvectors here are this column here, and this first column here. So this eigenvector is related to this eigenvalue. So the first eigenvalue, first eigenvector, second eigenvalue, second eigenvector is this second column here. And the eigenvector that we are interested is the one that is related to the principal eigenvalue. So the third one here, right? So you see that it's 0.8, 0.4, 0.3, okay? So if I take this last eigenvalue here, right? So this last eigenvalue is ID's one third column, right? So let me print this one here, okay? So the last one here, okay? So this one here, okay? 0.8, 0.4, 0.3, okay? If I divide this by the sum, okay? So because this don't sum to 1, okay? If I divide them by the sum to make it sum 1, just like we did with the populations, right? What are the proportions, right? So this is 0.53, 0.26, 0.2, okay? I didn't print the proportions here, right? Let me print the proportions. So the proportions here, now let me print the last line here. What were the proportions after a long time here? 0.53, 0.26, 0.2. 0.53, 0.26, 0.2. You see? So for a long time, the stable age distribution will be the eigenvector associated to the principal eigenvalue, right? So it would have told you all about the solution for a large time without ever simulating, just by analyzing the matrix of my system. Yeah, nice. So, okay. So I'm going to stop here. Here I have some explanation for people that have taken linear algebra. Okay, if you haven't taken linear algebra, just ignore this. Doesn't matter. Okay, but if you don't remember exactly why this happens, I go over the calculations to prove that for a long time this is dominated by the main eigenvalue and so on. Okay, so if it's not obvious for the people that took linear algebra, I have the derivation here, okay? And then we go back to generalizations on a later class, okay? I think it's time for today, yeah? Yeah, okay, we have gone over a little bit, okay? So that's it for today. Any more questions? Later, okay. Yes. Questions for general questions? Okay, so we stop here. Thank you.